Okay, everyone, welcome back to our Calculus 3 class notes. We're in section 15.8, last section in chapter 15, and we're on page 107. And we're finally to the point in discussing substitutions in multiple integrals, which really means how to transform our multiple integral to a different coordinate system by going through an example of a double integral. So in example 94, let's find the Jacobian for the polar coordinate transformation, x equals r cosine theta, y equals r sine theta. So what I'm trying to do here is to show you how this mathematical transformation is the same thing as understanding the polar coordinate system and transforming the double integral the way I've showed you geometrically prior. Okay, so then we're going to use the substitution theorem for double integrals to write the Cartesian integral over r of f of x y dx dy as a polar integral. Okay, so first of all, we need to find the Jacobian. The new variables are r and theta, not u and v, so that's okay, but r and theta. So we want the Jacobian of r and theta, which is the partial of xy with respect to the partial of r theta. And I remember that's notation for the Jacobian, which is a 2 by 2 determinant. So the first row is all the partials with respect to x, so partial of x with respect to r, and then partial of x with respect to theta. Second row is the partials with respect to y, so partial of y with respect to r, and the partial of y with respect to theta. So those are simple derivatives. So partial of x with respect to r is just cosine theta. Partial of x with respect to theta is minus r sine theta. Partial of y with respect to r is sine theta, and the partial of y with respect to theta is r cosine theta. So when I do the 2 by 2 determinant evaluation, I multiply cosine theta times r cosine theta, and I get r cosine squared theta minus the direction of the off diagonal. So sine theta times minus r sine theta is minus r sine squared theta, but it's minus that, so it's plus r sine squared theta. Factor out an r, I get r times cosine squared theta plus sine squared theta, and that equals r. So that's our Jacobian, which remember our integral becomes r dr d theta, so this is the r, which comes from the Jacobian. And then I have the integral over f of x y dx dy over r is the same as the integral of f of x, which is r cosine theta, y, which is r sine theta, times the absolute value of the Jacobian r. But since r is defined as being always positive or 0, I can drop those absolute value signs. So it's just this right here. So theoretically, what we're doing is when we're looking at a domain like this in y and x, for example, I let this go from 0 to 1 just to make it a unit circle, the quarter unit circle here. But the bottom line is, when we're looking at this guy, we really have to think of it coming from this type of rectangular region, G, which has the r theta coordinate system. So going from 1 in r to pi over 2 in theta. So from 0 to 1 in r and 0 to pi over 2 in theta. So in other words, a rectangular coordinate system in terms of r and theta was transformed into this polar coordinate system, and I get that double integral now, which makes it very easy to do. So the equations x equal r cosine theta, y equals r sine theta transform G into r. The Jacobian factor r scales the differential rectangle dr d theta in G to match with the differential area element dx dy in r. Okay, now it seems weird because we're contemplating this deeply, this substitution, but the integral here over G of f of r cosine theta r sine theta times r dr d theta is not the integral of f of r cosine theta r sine theta over a region in the polar coordinate plane. It is actually the integral of the product of f of r cosine theta r sine theta and the Jacobian r over this rectangular region G in the Cartesian r theta plane. This is in fact exactly how we've evaluated these integrals, but thinking of it in terms of the Jacobian makes it seem awkward at first.